Okay, let's begin. So, these are the examples we want to finish up. I'm going to take most, if not all, of the class to get through this, because not only is getting through these examples important, there are a lot of lessons that we can learn as we go through these examples that I would like to point out. That being said, let's jump into it. What do we remember? So, moving on to problem 5. So if you had y equals x plus 1 over x plus 2, how do you go about finding the derivative? What do you think? Quotient rule. Right. So it's like a derivative, a division. So that's your f, that's your g. You automatically know to find the derivative. It's going to be f prime g minus f g prime over g squared. So you need to have that rule that this is what the derivative of f over g looks like. So you see something divided by something else. Most generally, you can use the quotient rule. So, what is f prime here? 1. So we know how to differentiate x. That's 1. Derivative of 1 is 0. Times g. And our g is just the x plus 2. Minus, now I leave the f alone, which is x plus 1. Then I multiply by the derivative of g, which is? It's also 1. All over, well, g squared. So one thing you'll notice here is that I can actually simplify the top, x minus x. Then I would have 2 minus 1, so it just becomes 1 over x plus 2 squared. Hopefully you got that when you tried it. 6. Alright, how did you do this one?
Quotient rule? Oh wait, no, you can't, sorry. Wait, yeah.
You could, but you wouldn't.
Ah.
There's another way to think about it.
X squared to the negative 1, negative 1 power, or 2 to the negative first power.
Well, here's the way you can think about it. That over 2 is actually like a 1/2 being multiplied by the x squared. Right? And it turns out we know how to differentiate a constant times a function. The derivative is just going to be what? It's going to just be the constant times the derivative of the function. So that's just x. So y prime equals x here. Okay, so now this brings us to a first lesson here. Don't apply the quotient rule if the denominator is constant. Pretty much what you're going to do is leave the denominator alone. And differentiate the numerator. So another way you could have looked at this is, oh, if I want to find the derivative of, say, x squared over 2, leave the over 2 alone, differentiate the top. You'll notice that the 2x's would cancel, you just get x. Right? Now it's a lot easier than going through the quotient rule. Here's, for some reason, why a lot of students mess up in this particular way. If they did the quotient rule, it's not that it's wrong to do it by the quotient rule. But if you did this with the quotient rule way, and you wanted to find the derivative of x squared over 2, what is it? It's going to be the derivative of the top times the bottom minus the top times the derivative of the bottom, which is going to be what? Huh? 0 over the bottom squared, which is 2 squared. Okay? Now, one thing that you will notice here is that this second term here, it's just going to be multiplied by 0 because the derivative of a constant is going to be 0. Moreover, and that's not the bad part, because if you simplify this, you'll eventually get back to the answer. The bad part is students commonly forget to put a 0 here. Now, I don't know why that is the case, but statistically speaking, more often than not, they actually rewrite the constant there. I don't know why it happens, but it happens. I've seen it like so many times, right? They forget to put a 0 for the derivative. So oftentimes it's saying x squared times 2. Or if I gave them something like the derivative of x divided by, say, e squared, or something like that, x squared divided by e squared. Then they would say, okay, it's the derivative of the top times the bottom minus the top times the derivative of the bottom, and then they'll do something like a 2e here, which is of course incorrect, over the bottom squared, right? What they really should put here is a 0. But it turns out when you're trying to do the quotient rule, your brain is trying to process so many things. I think things can get dropped along the way. Like when you make something more complicated than it has to be, your brain just drops things. I don't know why it does that, but it actually does that. It's much easier to just leave the denominator alone and deal with the top, as opposed to going through this whole thing where now you have an option of forgetting something. So in the worst case scenario, you're going to forget that that's a 0, because I've seen it happen thousands of times at this point. Students forgetting to put the 0 here. And in the best case scenario, you just went through something that's totally useless because it's 0. It's not going to matter anyway, right? The only part that's going to matter is this first part, right? So this is just something extra. And if your function is complicated enough, that extra part could be like something like huge. But at the end of the day, you're going to realize that all the 2's cancel and you're just going to end up with x anyway. You might as well get it a lot easier. Yeah?
For the other one, the derivative of e squared
Is 0. E squared is a constant.
Yeah, that makes sense. I was thinking about e to the x and how to.
Right, so the derivative of e to the x is not a constant because of the x.
Okay, so that would be.
Right, so if I were to graph e squared, it's a horizontal line passing through e squared.
Okay.
If I were to graph this, it looks like that. They're very different things. So things like that, those little nuances, it's very important to pay attention to them, and it just so happens that for some reason, a nuance like this is a lot to process sometimes. But yeah. So technically the quotient rule, it's not that it's wrong, it makes it more complicated than it has to be, right? Just ignore the bottom, deal with the top, as opposed to going through this whole thing where even if you pull it off and you get it right, you just wasted time computing some useless term. So that is the first thing. So like I said with the chain rule, it actually doesn't matter if you use the chain rule all the time. It doesn't actually make things worse. But there are times when the quotient rule can make things less efficient. And the product rule can also make things less efficient, right? So for example, if you rewrote this here and there's a constant times a function, technically you could have done the product rule here, but again, why would you? We have a rule that says just leave the constant alone and deal with that part. So there are times when you probably don't want to use a quotient rule. And one situation in which you don't want to use a quotient rule is if the denominator is a constant. So that's just one thing that can save you a lot of headache that I have to point out, because a lot of innocent students fall prey to this. Breaks my heart. What about 7? How'd you do that one? Did you do the quotient?
No.
You're just saying that because I did this all day. Okay, this is another, yeah.
It's 3 x to the negative 1/2.
Right, you can rewrite this as 3x to the negative 1/2. right? So that's the function. And now you can differentiate it using the power rule, which you know. Bring the power down, subtract 1 from the power. It's easy. So that's probably another thing that I would say. If the numerator is a constant, I wouldn't apply the quotient rule either. For the same reasons as before. Don't use quotient rule. If numerator is a constant. How do you deal with it? Just bring up the denominator. Plus you know how to do that. Raise it to the minus 1 power by the laws of exponents. And then what you do is apply the power rule or the chain rule. And you're usually, it's gonna end up easier than going through the quotient rule. A situation where you'd have to apply the chain rule, I don't think I did it here, but for example, if you had something like differentiate 1 over the square root of x squared plus 1, right? Now, yes, it's a division, but the numerator is a constant. What I would do is I would think of this as, just bring the bottom up, write it as a negative 1/2, and now that's something where you need the chain rule. There's just an inside function, so you differentiate the outer function, multiplied by the derivative of the inner function, 2x, and that's your derivative. So this 2's would cancel, you get minus x times x squared plus 1 to the minus 3 over 2. So you don't actually need the quotient rule there. So if your top is a constant, just bring the bottom up, raise it to the negative 1 power. Sometimes you'll be able to use the power rule after that. If not, it's just going to be a chain rule situation. Just move the power outside of whatever the complicated mess is, multiply the derivative of the inside of the mess. So it's usually more efficient if the denominator or the numerator is a constant not to use the quotient rule. Not because it's wrong, but statistically speaking, students get it wrong more often when they try to use the quotient rule in these situations than not. 8. Okay, so how do you differentiate this? Yeah?
How you rewrite it as 4x to the negative 3, and then do the product rule, so negative 12x to the negative 4.
Yeah. That's your derivative. So these situations here, at first glance, they might look like a quotient rule situation, but because the denominator or the numerator is a constant, I wouldn't use a quotient rule. It means you can rewrite them using your laws of algebra and use actually a simpler rule. Which actually goes back to a tip that I gave you last class. You kind of want to try to simplify things before you even need to use the calculus rules. It might actually help you get away with certain things. Moving on to 9. Ln x divided by e to the x, how would you do that?
Do we have to use a quotient rule? Because the denominator isn't a constant, and neither is the...
Right, so neither the numerator or denominator is a constant, so I probably want to just think of these as two separate functions. That's an f of x, and that's a g of x. So I know that my y prime is going to look like f prime g minus fg prime over g squared. And of course, until you memorize the rules, write them down every single time you're using them. eventually you would memorize them. Or have your own little mnemonic or a sentence. Like in my head, every time I'm doing the Quotient Rule, I literally say a sentence in my head. Like, it's the bottom times the root of the top, and it's the top times the root of the bottom over the bottom squared. Like I literally like say out that whole sentence, right? Which seems silly when I tell you that's what I do. Why don't you just memorize the formula? You're a math guy. Like why would you go? But it's actually that's a pro tip right there. Whenever you're learning anything technical, math or otherwise, the better you can get that to coincide with your language, the more you'll actually understand it. You actually increase your cognitive powers by actually making what you want to understand a part of your own language. And it's funny, sometimes while I'm like tutoring someone, like I notice these things, like if their native language is Spanish and I ask them to like, oh, they're doing some arithmetic, they actually say it in Spanish, oh, cinco, seis, I'm like, oh, okay, right? They think in terms of their language, and it's a pro tip. Chances are, if there's something you misunderstand, you're not able to talk about it, right? So you're like, I don't get this, okay, tell me what you think about it. Just like in English, you won't be able to do it. The moment you actually learn to talk about that thing in English, you'll understand it on a technical level automatically. It's crazy how that works out. So yeah, don't laugh at me. It's actually it's a tip there, just for your studying. It helps you in math, helps you in everything. If you don't understand something, learn to talk about it in like everyday language, like you're talking to a friend. Could you say it in English? It means you don't understand it on the technical level. There's a podcast. It's really interesting to listen to. It's old. I think it's a Radiolab podcast from NPR, and it's called Words. Right. And it's literally about what I'm just talking about, how your language affects your cognitive abilities. And it's like, they tested some adults and they took away their abilities to use words, right? Like they hooked something up to their brain, or they just put them in a confusing situation where they can't speak. And it's like, their intelligence reduced to the level of like a toddler. They couldn't like get through the simplest of mazes. Like they totally like couldn't think. It's like they got lost in the most silly, it was crazy, right? Just like taking away your ability to use words literally takes away your ability to think. So that's a problem. If you want to learn something very well, learn to talk about it. So there are times when I'll memorize a formula, I literally memorize it as a sentence. But at the end of the day, however you memorize it, you need to have this formula memorized. So f, I'm going to take the derivative of f. We learned what that was last time. What is that? Derivative of ln x.
1 over x.
It's 1 over x. And the derivative, and g, well that's just e to the x, minus the f, which is the ln x, times the derivative of the g, derivative of e to the x, e to the x, that's itself, all over e to the x squared. Now that's that. You can simplify that a little bit though. E to the x is a common term. I can factor that out. And of course, this will cancel with that. So I can do something like 1 over x minus ln x over e to the x. And I'm fine with that. If this were your textbook, it wouldn't write the answer that way. It would probably not like the fraction inside of a fraction. So you could multiply this by x over x and write it in another way. 1 minus x ln x over x e to the x. So that's an alternative for it. But I wouldn't really care. As long as you cancel all the common factors, in general, I won't care. 10. E to the x times ln x. So what rule would apply here?
Product rule?
Product rule. This here looks like one function f, that here looks like one function g, and neither of them are a constant. If one of the things was a constant, I wouldn't really do the product rule, I'll just do the constant factor rule. Leave the constant alone, differentiate the function part. But as it stands, the rule that I want to apply here, if y is f times g, then this is going to be f prime g plus fg. So I'm just going to go through here. So this means y prime is going to be equal to, so f is e to the x, f prime is e to the x, g is ln x, plus f is e to the x, times the g prime is 1 over x. So, in fact, I need to do this, but it's not totally necessary. Usually, you really care about factoring stuff out if you want to like cancel stuff. Otherwise, it's not really. Either one of these is fine. So 10, product rule, because it's a product of functions, neither of them constant. 11. How do you do that one? Chain rule, right? So you don't want to expand the 20th power. That's not going to be fun. But you notice that there's an inside and an outer function. So what we would do here is apply the chain rule. And how would it be applied here? What did you get?
I got 20 times, open parentheses, x cubed plus 1 to the 19th power
Mm-hmm.
times 3x squared.
Right. So it's the derivative of the outer function multiplied by the derivative of the inner function. So the outer function is a 20th power, so we can use the power rule for that. Bring the power down, subtract 1 from the power, so you end up with this. Leave the inside alone in the first situation. Sometimes students decide to start differentiating here. That's incorrect. Leave the inside alone. Afterwards, you multiply by the derivative of the inside. And yeah, that's going to be that. You could now simplify this a little bit by taking the 3x squared times the 20, so that's 60x squared times x cubed plus 1 to the 19th. And that's going to be your derivative. Questions on that?
On the test, could we leave the answer the way that you had it before, or do you want us to like just?
For something like this, it's fine. If you
Okay.
left it the other way. There are times when simplifying is going to be important, but probably not so much in this context. 12. How do we do that one? Yes? Yes.
So you want to do the chain rule, so first e to the x cubed plus 1, because e to the x is derivative is e to the x, and then times 3x squared.
Okay. Can you tell me the rule that you were applying?
The chain rule?
Yeah, but we actually memorized that as a formula for this particular case. Do you remember how we thought about it? Yeah.
P times u prime.
So the whole rule
D
starts with this.
x equal e to the u equals u prime times u.
Yes. So yes, we derived that by the chain rule. And if you say think about it, so completely fine. Another way to think about it is just we have like a formula for this specific situation. So the x cubed plus 1, I could just think of that as a u. And so as Ava said, it's going to be, at the end of the day, it's e to the u, which is x cubed plus 1, and then you multiply by the derivative of u, which we now know is 3x squared, by the power. So the derivative of e to anything is the derivative of the thing times the original function. 13. How do you deal with that one?
U prime over U.
U prime over u. So the entire rule for this one, again, derived by the chain rule. But it says if we want to differentiate ln of something, it's going to be the derivative of the thing over the thing itself, u prime over u. And in this case, that guy here is our u. So this would mean, just by following that rule directly, what's the derivative of this?
3x.
That's using the power rule over that thing, x cubed plus 2x plus 1. That's going to be the derivative. I see you differentiate that. How do you do it?
Chain rule.
Chain rule? Okay, how does it apply to?
So you do the derivative of the outside function, which is 1 over 2 root 2 minus x squared times the derivative of the inside function, which is negative 2x.
Times the derivative
Of the inside function, which is negative 2x.
minus 2x. So the derivative of the 2 is 0, the derivative of the minus x squared is minus 2x. So this one, it's pretty much minus 2x over 2 radical 2 minus x squared, plus the 2 squared. So that's that. So you'll notice in these problems, and I guess problems in general, they're kind of all testing how well you know the rules. Do you know how to apply the chain rule to this thing? Do you know how to apply the product rule to this thing? At the end of the day, when it comes down to computing derivatives, that's what it's about. Eventually we're going to learn how to apply. What's the use of being able to do this? It's a neat trick, but is it useful? It's actually very useful. But at the moment, we just want to know how to get to derivatives, and later on we're going to learn how do you actually put them to good use. How would you do that? Yeah?
So you do the quotient rule.
Quotient rule. And so here, notice that this here is a one function f, that here is another function g. So the quotient rule says what?
G times f prime
Well,
minus
f over g equals.
f prime times g minus g prime times f over g squared.
Right? So that's the rule you have in your head, that's the template. You're literally going to be plugging these functions into that template. So at this point, your y prime is going to be equal to
1 times x plus 4 to the 6th times 1 times x plus 1
minus,
or minus x plus 1 times 6 x plus 4 to the 5th all over x plus 4 to the 6th times 2, or to the 2.
now How did you actually differentiate this part over here?
I'm using the chain rule.
Alright, so notice that you need to apply the chain rule here. Now, the derivative of the inside is actually 1, so technically there was that there, but we didn't have to write it down. So you differentiate the outer function, multiply by the derivative of the inside, so a chain rule actually applied there. Now at this point, we want to simplify a little bit. So notice what we have is we have x plus 4 to the 6 minus 6x plus 1, x plus 4 to the 5th, and on the bottom is x plus 4 to the what? The 12th, so we know that that we would multiply that. How do I simplify?
On the top, we factor out x plus 4 to the 5th.
Right. So you factor out the common term to the lowest power to which it appears. What would we have left over?
X plus 4 minus 6 times x plus 1.
Right. So there were 6 factors here. We pulled out 5, so there's 1 left over on the inside. There's a 6x plus 1. We didn't do anything, but we pulled out all 5 factors out here. So that's what left over in there. Now here we have x plus 4 to the 12th. This is going to allow us to cancel 5 of these guys, leaving us with power 7 here. Now, inside the parentheses, notice what I have is that I have x plus 4 minus 6x minus 6. I can actually combine those. I don't know if you can see it here. So it's x minus 6x, that's minus 5x, and then plus 4 minus 6, that's minus 2, all over x plus 4 to the 7th. That's going to be the answer. So you simplify that in the quotient rule. Right, so you want to simplify a fraction. So remember from pre-calc how that's done. Basically, factor out common terms from the top and the bottom and cancel any ones that are common to the top and the bottom. Yeah, all right, moving on. 7:16. How do you do this one? Quotient rule, it's another division. So that's like my f, that's like my g. And I know if I want to differentiate f divided by g, it's f prime g minus f g prime over g squared. So now I'm going to start plugging these guys all in. What's it going to look like?
One minus e to the x to the third minus x times e to the x to the third times 3x squared over e to the x to the third times the root of 2 times. So square that.
Okay. Simplify.
Can you simplify the e to the x cubed?
Yeah, what do you do with it? What do you have left over inside? 3x cubed e to the x cubed squared. This guy cancels that. And that's your answer there. Let's keep going. $17. Okay, girl, how do we do this one?
I said oof.
Oof.
Chain rule and product rule.
Chain rule and product rule. Why do you think product rule?
Why?
Notice here, we have two functions being multiplied. So I realize now I'm going to have to use the product rule. Now for the product rule, eventually I'm going to have to differentiate each of these guys individually, and that's where the chain rule is going to come in. But I do know that the derivative of f times g is f prime g plus f times g prime. And furthermore, for each of these, here, we are going to need the chain rule here, and we're going to need the chain rule here. You won't need it in general, but in this case, you're going to need it. So, look at a problem. The first thing you want to identify is what rule applies to this problem that I'm looking on. It looks like two things multiplying each other. The product rule seems to make sense. Neither of the things are constant. Then you're going to regurgitate what is the product rule. If you have to write it down, just write it down. So now you're going to take these templates and you're going to plug these guys in. So here, what would f prime look like? And then?
Plus x squared plus 1 to the 5th. No.
Times?
X squared plus 1 to the 5th.
Yeah?
Plus.
2x plus 1 to the 8.
Times 5 times x squared plus 1 to the 4th times 2x.
So if I made you simplify that, how would you do it? It's going to come in handy for the next problem. But yeah, how do you do that?
First, can you combine the constants? So you get 16 times 2x plus 1 to the 7.
Yeah, but that's actually going, you'd probably have to undo that to simplify it further.
Then you would factor out the
You just want to factor out common terms,
and
right?
x squared.
Now the
plus
2 is already a common term and it's already exposed, so I probably wouldn't want to combine it with anything and then I visually lose that q that is a common term. So first you go through, you identify all the common terms, 2 happens to be one of them. Another common term is of course the x, 2x plus 1, 2x plus 1. Another common term is the x squared plus 1, x squared plus 1. Anyone else that's common? No. So what we're going to do is we're going to factor out the lowest power of all the common terms. So of course, 2 gets pulled out. I'm going to factor out the 2x plus 1 to what power?
This 7, Bob?
7. X squared plus 1 is also a common term. Factor out what power? 4. Those are all the common terms. So now I open brackets and I'm going to write what's left over. So in the first situation, the 8 gets left over. 2x plus 1 to the 7, I pulled out everything, so that's gone. The 2, pulled that out, that's gone. There are 5 factors of x squared plus 1, I pulled out 4 factors, so there's 1 factor left. Plus what's left over in the second part.
2x plus 1.
Is X left over?
That's what that's going to look like. Now, of course, inside here, I can clean this up a bit. What's in here? This is going to be 8x squared plus 8. This here is going to be 20x squared plus 5x. So this now gets simplified to 2 times 2x plus 1 to the 7 times x squared plus 1 to the 4 times 8x squared plus 20x squared, that is 28x squared. And then I would have 5x plus 5x, then I would have 8. That's that, guys. Do. Start off with 18. Try 19 for Friday. Practice. What if I had the derivative, the divisions of them? How would you do with this? Quotient, right? So think of the top as the F, the bottom as the G. And so y prime would equal to bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So you want to simplify these, you kind of do the same thing that we did there. You're going to pull out the common factors, which we know is 2 times x squared plus 1 to the 4th times 2x plus 1 to the 7th. And we would be left over with 8 times x squared plus 1 minus 2x plus 1 times 5x. Now, this guy cancels with 4 of those guys. On the inside here, we would have 8x squared plus 8 minus 20x squared minus 10x. And this gives us 2 times 2x plus 1 to the 7th times minus 12x squared minus 10x plus 8 all over x squared plus 1 to the 6. What's that one? Try 19. We'll pick up with that on Friday and then learn a whole other differentiation technique. That's going to be fun. See you guys.